Welcome to this hands-on AI vision project where we turn ordinary video into intelligent posture insights. In this tutorial, you'll learn how to use Ultralytics YOLOv8 Pose Estimation to detect body keypoints, calculate spinal bend angles, and identify hazardous postures, all in real time. We'll walk through each step, from installing dependencies, analyzing keypoints, to triggering live alerts via MQTT. Whether you're working in occupational safety, physical therapy, sports science, or factory automation, this project gives you a real-world template for posture intelligence. So grab your coffee, load your dataset, and let's turn computer vision into ergonomic action. In the first step, we prepare our Python environment. Using pip, we upgrade to the latest package manager and install the Ultralytics YOLOv8 version 8.3.121. This version supports pose estimation and tracking. Alongside it, we install OpenCV for video processing, Pandas for data analysis, and Matplotlib for visualization. These libraries work in tandem. YOLO detects and tracks poses, OpenCV handles frame-by-frame input, Pandas organizes the output into structured formats, and Matplotlib allows us to analyze trends such as bending angles. This setup is essential for high-performance pose detection in both static analysis and real-time applications. It's the foundation on which all subsequent steps are built. Once installed, we're ready to upload our input video and start extracting pose data. This marks the beginning of building a posture intelligence system capable of identifying risk through advanced AI and computer vision. Now, we move into the core pose detection step. Using the YOLO-v8x-pose.pt model, which is the most accurate among the YOLO variants, we process a video called input.mp4. The model.track function is used to analyze each frame and detect human keypoints. We enable two output options, saving an annotated video and generating raw text files with pose keypoints for every person in each frame. The confidence and IOU thresholds are set to fine-tune the detections. The system detects up to 2 people per frame and records their postural data with speed, processing each frame in under 40 milliseconds. This sets the stage for the deeper analysis we'll perform later, giving us both visual confirmation and machine-readable output. With this step, we bridge raw video footage and structured human movement data, building toward automated ergonomic risk evaluation. Once we've run the YOLO tracking, it's time to convert the results into a structured data format. This step extracts the X, Y coordinates and confidence scores of 17 keypoints per person in each frame. A loop iterates through each detection and writes the data into rows representing individual persons in specific frames. The result is a CSV file with 53 columns, 1 for frame number, 1 for person ID, 17 for X coordinates, 17 for Y coordinates, and 17 for confidence values. This tabular data structure enables us to perform advanced analytics, such as angle measurements, filtering hazardous posture events, or long-term health tracking. The assert check confirms the format's integrity. This CSV becomes the foundation for detecting posture anomalies in a scalable, automatable way and can even be used to train models or visualize body movements in time. In this step, we analyze the posture angles to detect risk. By calculating the angle between the left shoulder and left hip, specifically keypoints 5 and 11 from the COCO format, we estimate the degree of spinal bend. Using the arctangent function, we convert the position into a physical angle. If the angle exceeds 60 degrees, we classify the frame as hazardous. These frames are extracted and written into a new file, hazards.csv. This method is critical in workplace safety and physiotherapy, where spinal posture directly affects health. With simple geometry, we translate body landmarks into actionable safety metrics. This step transforms raw data into intelligent flags, ideal for triggering alerts or storing historical ergonomic violations. The result, automated safety assessments from video footage using just a few lines of Python. Next, we bring visual insight into our spinal bend angle data. Using Matplotlib, we generate a histogram that shows how frequently different bending angles occur throughout the video. The distribution helps us understand overall posture trends, whether most workers are within safe limits or frequently entering risky ranges. Each bar in the histogram represents a range of angles and how many frames fall within that range. Peaks in risky regions, especially beyond 120 degree, can flag deeper systemic problems in workflow or workstation setup. This type of data visualization is critical not only for engineers and safety analysts but also for conveying insights to non-technical stakeholders. It allows us to validate the effectiveness of posture training, ergonomic improvements, or AI-based safety systems. From video to dashboard, this visual closes the analysis loop. Let's now scale up the application for real-time environments. This architecture diagram shows a production-ready system that uses RTSP-enabled IP or USB cameras feeding into a GPU box or Jetson module. The live stream first hits a gateway that converts RTSP to WebRTC for browser-based viewing. It's also passed into a Pose inference engine that computes keypoints in real time. Then, results are routed through an event router. This router can either publish messages to an MQTT topic labeled pose/hazard, or store time series metrics in timescale dB. A Grafana dashboard visualizes everything. This pipeline supports deployment on manufacturing floors, hospitals, or rehabilitation centers, allowing live monitoring of workers or patients. It also enables integration with and lights or PLCs to trigger immediate responses in case of detected hazards. The design is modular, scalable, and field deployable. Here, we implement the logic that powers real-time alerting. We define a function to calculate spinal bend angle using average positions of mid-shoulder and mid-hip keypoints. For each person detected in each frame, we check if their bending angle exceeds 60 degrees. If it does, we construct a JSON event with the camera name, timestamp, bending angle, and hazard flag. This event is then published to the MQTT topic pose/hazard. This lightweight messaging protocol enables real-time integration with dashboards, control systems, or cloud-based loggers. It's ideal for edge AI deployment where latency and efficiency matter. This function closes the loop from vision to action, enabling automated alerts or preventive responses like warning sounds, lights, or push notifications. Finally, here's a preview of our structured dataset. This snippet shows the first few rows of the Keypoint CSV, where each frame and person ID is followed by their 17 joint X coordinates. This format makes it easy to plug into statistical models, feed into machine learning pipelines, or visualize pose trajectories. By turning unstructured video into rich, numerical data, we unlock endless applications, athlete performance analysis, ergonomic optimization, and even clinical diagnostics. Every row is a snapshot of a person's posture at a specific moment in time, ready for intelligent processing. That wraps up our journey from video frames to real-time posture analytics. With just Python, YOLOv8, and some well-structured logic, you now have a powerful tool to detect spinal bends and trigger alerts when people move beyond safe angles. This system can scale, from a simple CSV log to a live edge device with dashboard integration. If you found this valuable, give it a thumbs up, subscribe for more real-world AI projects, and share it with anyone passionate about safety and human-centered design.